Cool, yeah. So I want to talk to you today a little bit about some work I did during my PhD on the additive manufacturing of sustainable oxygenated polymers. So additive manufacturing, or more commonly known as 3D printing, is a really powerful means to quickly and cheaply produce complex parts and shapes that are really challenging to produce through conventional manufacturing techniques. You're probably most familiar with material extrusion-based 3D printing. This is really commonplace now. It's widespread, it's affordable, it's relatively slow, and it results in poor printing resolutions. Another type of 3D printing, which is a bit less well-known, is this vat photopolymerization, where we use a UV light shining up onto a vat of a photoreactive liquid polymer resin. And that allows us to cure that resin with spatial and temporal control and produce parts quickly and with really smooth finishes. And this is already being used widely to produce a range of different products, from healthcare to sportswear. However, the majority of these materials are derived from petroleum, and therefore they have limited end-of-life options. In my group, or in our group, we are particularly interested in trying to find sustainable alternatives to these. And we like to do this through a range of different polymerization techniques, but mostly through the ring opening polymerization or the ring opening copolymerization of monomers that can be derived from biomass, or in the case of my PhD and my research, looking at directly polymerizing carbon dioxide to form polycarbonates. Obviously, CO2 is a really attractive monomer. It's cheap, it's overly abundant, and we find a way to utilize it, we can valorize it. So I'm going to walk you through our synthetic plan here. If you're not super familiar with looking at these kind of structures, don't worry. I'll try and keep it as simple as possible. We first carry out what we call the ring opening polymerization of this lactone, shown in green, to form this polyester. And this monomer can be derived from castor oil. And then by playing a neat little trick with our catalyst that we use, we can switch the reaction atmosphere from nitrogen to carbon dioxide and trigger a mechanistic switch within our polymerization. So we shut off the ring opening polymerization of the lactone, and we start the ring opening copolymerization of carbon dioxide and this vinyl functional isopoxide. We can then exploit that double bond with a multifunctional thiol to cross-link our material and carry out our digital light processing printing. Then we can wash up these parts and hopefully have some nice 3D printed shapes with this structure. And specifically, the crosslinkers we were looking at were these three here, which we called X1, X2, and X3. Whereas we go from 1 to 3, we increase the length of polyethylene glycol in the crosslinker. We increase, hopefully, the hydrophilicity of that material. So to turn these chemdraws into reality, I made this. For this kind of printing, you need quite a lot of material, so we produced 204 grams of it. So here's the synthesis. You can see it's a lovely colorless liquid. And then through some optimization, we were able to print this. And here is the first successful print, which was a very exciting day. And you can see we've just produced some very simple specimens for thermomechanical testing. So it's a reminder that as we go from P1X1 to P1X2 to P1X3, we're increasing the length of that crosslinker and hopefully its hydrophilicity. If we look at some mechanical testing of these materials and we pull them apart, we can see there's not really much difference between the crosslinkers and the mechanical properties. We do see a decrease in elastic properties as we increase the crosslinker, and that's attributed to the fact that we've got an increased number of degrees of freedom and therefore more hysteresis. We do observe the expected increase in hydrophilicity, and we can look at this through water swelling experiments as well as water contact angle experiments. And as a result, we can tune the degradation of these materials. So the higher the hydrophilicity, the faster the rate of degradation, which could be open up really exciting opportunities in biomedical applications. So we had a look at some cytotoxicity experiments and saw no initial cytotoxic response for these. Finally, we wanted to test how good the resolution was that we could achieve with this resin. So we printed some more fun structures, in particular these triply periodic gyroids. You can see the smallest one here is just 3 millimeters tall. And here in the CT scan of it, you can see that we maintain really good resolution of these small details, in particular the internal holes and cavities. So to conclude, we've been able to produce a new polymer for this type of 3D printing with a really high renewable content. We can print it really successfully. We can tune the hydrophilicity, which ultimately gives us tunability on the rate of degradation, which we think could be really important in using it for regenerative medicine. So and we see there's no cytotoxic response. So this is our sort of future directions of thinking with this project. And finally, something I've not talked about is this observed effect of printing-induced phase separation, which we think could be really important for producing the next generation of 3D printed materials. So I want to conclude by thanking my amazing supervisor, Professor Charlotte Williams, my amazing group, and our collaborators led by Professor Matthew Becker out at Duke University, who helped us achieve this 3D printing. Finally, I'd like to thank you all for your kind attention. Thank you.